All right, let's dive into a pretty mind-bending idea. What if the limits of what we can compute aren't just about logic, but about the actual laws of physics? Today, we're going to trace that thought all the way from the simple, beautiful concept of a computer to the seriously strange and powerful world of quantum reality. It's a journey that forced us to change everything we thought we knew. Back in the 1930s, with the legendary mathematician Alan Turing, he came up with an idea that would literally become the blueprint for every single computer that followed. He pictured this really simple, abstract machine. All it had was a long strip of tape, a little head that could read and write symbols on that tape, and a set of rules. That's it. But this Turing machine was a universal concept. It was so powerful that it could, in theory, compute anything we'd consider, well, computable. It is the direct ancestor of the very device you're watching this on right now. This idea was so massive that along with work from the American logician Alonzo Church, it became known as the Church-Turing thesis. And for computer science, this was like the law of gravity. It basically said, if a problem can be solved with an algorithm, a Turing machine can do it. For decades, that was the line. That was the absolute limit of computation. For a long, long time, that was the end of the story. Computation was this neat, clean field of abstract logic, totally separate from the messy, complicated world of physics. But then, reality came knocking. You gotta love this. In the early 80s, the physicist Richard Feynman stood up and pointed out a massive problem. He realized that our best computers, these incredible Turing machines, were actually terrible at simulating the universe. And why? Because at the most fundamental level, the universe doesn't play by classical rules. It's quantum. And this created a huge gap. I mean, the very tool we use to understand the world couldn't even model its basic operating system. It was like trying to run modern software on a steam engine. The model was breaking down because physics and computation just weren't speaking the same language. So this problem really set the stage for a revolution. And in 1985, a physicist named David Deutsch looked at this whole mess and came up with a solution that was so radical, it changed everything. See, Deutsch didn't just tweak the old idea. He totally reframed it. He argued that computation isn't just some abstract game of math. It's a physical process. It happens in the real world. So our ultimate computer has to be able to simulate any physical process in the universe. And that means it has to follow the rules of quantum mechanics. This slide just nails the shift in thinking. We went from seeing computation as pure, abstract logic to understanding it as something deeply physical. If the universe runs on quantum code, well, then we need a quantum computer to tap into that power. The Turing machine was brilliant, but it wasn't the final word. Okay, so what can this new kind of computer, one that's built on the laws of physics, actually do? Where does it get all this power? Well, the answer is in harnessing the beautifully weird rules of the quantum world. The first secret ingredient is something called superposition. You know how a classic computer bit is either a 0 or a 1, a light switch, either on or off. Well, a quantum bit or a qubit can be a 0, a 1, or kind of a blend of both at the exact same time. It's like a dimmer switch existing in this fuzzy cloud of possibilities until the moment you look at it. And this table really gets to the heart of the difference. A classical computer chugs along one calculation at a time. That's serial processing. But a quantum computer, because it uses these qubits in superposition, can explore a mind-boggling number of possibilities all at once. And that right there, that's the magic trick. It's called quantum parallelism. You can set up your input as a superposition of a ton of different values, and when you run an operation, it acts on all of them at the same time. It's like having millions of parallel processors all crammed into a single quantum state. So calculating all the answers at once is just step 1. The real genius is step 3, quantum interference. Think of it like waves in a pond. The algorithm is designed so that the waves for all the wrong answers crash into each other and cancel out, while the waves for the one right answer build each other up, getting stronger and stronger. So when you finally measure the result, that's the one you're almost guaranteed to see. And this isn't just a nice metaphor. Deutsch laid out the exact math for this in his groundbreaking 1985 paper. He showed exactly how a single quantum process could get the results of what would take a classical computer countless separate calculations to achieve. It's all right there. Okay, let's pull all of this together. What does this new reality mean for those limits of computation we asked about way back at the beginning? The big idea, the main takeaway is this. Alan Turing's model was perfect for a classical world, but we don't live in a classical world. David Deutsch showed us that to build the ultimate computing machine, we have to build it out of reality itself. Computation isn't just an abstract idea, it's a physical process, and its only true limits are the laws of physics. And that leaves us with a really exciting question to think about. For decades, our computers were based on logic. Now we're learning to build them based on physics. And if information and reality are really two sides of the same coin, what new frontiers are we about to unlock? What problems that we've always thought were impossible might suddenly become solvable?